yeah, basically I'm comparing what DEAP calculates to what we've measured. So yesterday you got a good bit of information from PJ and Kai on more about how it was done. So I'll only touch on that. Just as a matter of interest, how many people here were here yesterday for that? So there's a few of you. So yeah, I'll mention how we've gotten some of the information as well then. So, see if this works. It does, great. Just to introduce then, I'll just give a quick overview of the monitoring side of SERV. I won't talk about the higher overview. An overview of DEAP, some DEAP statistics. I look at some comparisons then as to measured versus calculated, and we'll conclude then. So this is a graphic. The people who were here yesterday saw it. I'm not going to go into every box, but basically we had about 70 houses with a basic monitoring installation, 30 houses with a desegregated electricity installation. Out of those 30, 10 we looked at their domestic hot water, 6 we looked at their oil boilers, and 4 we looked at their solar panels. So, and all the rest of it is about the inputs, various inputs and outputs. So top lines would be the inputs to the basic system, and the bottom line is the outputs that we've got. And I think as we've gone along, we've come up with even more outputs. Because we're comparing a relatively small sample size to a national tool, I just included this slide just to give you an idea of geographical breakdown of the houses that we're monitoring in SERV. So you can see that's Lough Derg, very north of Tipperary there, and we've got Nina here. So there's about a 60-40 split on the locations of the houses between rural and urban. We also tried, when we were selecting the houses, to get a good mix of occupancy durations and I suppose just to have a kind of a fairly good mix of profile. So that's the graph on the right hand side there. You can see that we obviously didn't want to pick houses where somebody is only in the house for a few hours a week. It wouldn't tell us very much, but at the same time we did need some houses where it's just going to be, you know, evenings and weekends. So that's say number 2. That's number 2 there. So we had 22 of those where it's kind of evenings, weekends, people are away at work during the day and they come home. And then towards the right hand side then are the houses that are occupied more and more. So DEAP then, just to say a little bit about it for those of you who aren't too familiar with it, it's the Dwelling Energy Assessment Procedure. The quotes here are taken from the most up-to-date version of the DEAP manual, 3.2.1. So DEAP is compliant with the methodology framework in the EU EPBD directive, and its calculation framework is based on ISCN 13790, and it draws heavily from the SAP in the UK, which is its equivalent basically, SAP, yeah. DEAP is used to demonstrate compliance with the EPBD in Ireland for new dwellings. So that's the intro on DEAP. DEAP is a really comprehensive tool. It does an awful lot. And it has to cover the whole population. So I guess that's why we're going to see some of the differences between calculated versus actual consumption. So it refers to the ISCN ISO 13790. I'm sure you've all read it. And it has to make assumptions to get anywhere basically. So that's what we're going to be looking at now in a minute. The graphic on the right is your typical A to G rating. So DEAP, some of the assumptions, it assumes standard occupancy hours, heating run hours on boilers and patterns, the number of occupants don't impact, the number, type and control of electric appliances, standard climate data for the whole country, so your BR will be the same if you're in Offaly as if you're in Kerry. Ventilation then is calculated. building elements, you can go for default values if the assessor doesn't know what they're looking at. I'm sure lots of people here know plenty about the BR, but I said I'd include this. It's obviously more accurate if the assessor can access or get verifiable actual values rather than using the defaults. However, this isn't always possible. So ISO 6946 governs the U-value calculations. Domestic hot water is derived from floor area, which is, I suppose, is one of these necessary assumptions that have to be made. It, you know, I suppose your floor area, like if you've got 5 people in a house versus 1 person in a house, the 5 are going to use more water than the 1, but the house might be the same size. The internal temperature and schedule then, DEAP assumes you're heated weekdays and weekends from 7 until 9 in the morning and 5 until 11 at night. The required set points during these periods, the living area is 21 degrees Celsius and the rest of the dwelling then is 18. And it applies a floor area weighted average temperature then for the whole house. And the heating season is October to May. So space heating requirements, the seasonal efficiencies are taken from the HARP database, Heating Appliance Register of Performance, or a standard tables given in DEAP. Obviously, better again if you can get the more accurate figures rather than relying on the standard tables. Heating control types and responsiveness have factors associated. Carbon dioxide factors are given in the manual. Solid fuel heat, the worst case is generally assumed unless wood can be proven that, say that only wood can be burnt within the secondary heat appliance. DEAP assumes 33% of domestic hot water is from a back boiler, if present. Secondary heat in kilowatt hours per year from table 7 is 10% of the heat requirement. We'll look at that in later slides. So DEAP, the main theoretical outputs then, so we've got the delivered energy in kilowatt hours per year. So that's basically your energy bill. It outputs the primary energy, so that includes the overhead, basically, of getting the energy from whatever mine it's dug out of to your house, basically. So that's the primary energy, and that was one of the things that we had to be very careful about when comparing DEAP outputs to measured outputs, because measured is delivered energy versus DEAP giving primary energy, so it's an important one not to confuse. The carbon dioxide emissions are given then as well. The emissions are calculated on the basis of primary energy consumption. So basically it's assumed that oil or gas burnt at a power station to deliver your kilowatt hour of electricity is allocated to your house, and any losses in between are accounted for by your house as well. The SERV analysis status then, at the moment, this is just actually a snapshot from a slide yesterday by Kai. So at the moment, analysis of data from the database is ongoing by ECNet, one of the project partners. Kai isn't in the room, he must be upstairs. So data for the homeowners report, including SEI data, available mid-July. SERV data available primo, I guess that must be Danish, September 2012. The data analysis then is being done by Visual Basic, so it can be taken by others and played with and doctored, and that's something I think will be encouraging at later stages. And non-residential buildings, then the analysis there and build data is agreed and it's ongoing. So now I've just got some kind of statistics just to set the background on where we are in terms of kind of the SERV region versus the national. So you can see there, right, the red bars are kind of where the the serve houses were before they were upgraded. Okay, you've got your A, B up to G. The SEAI now, I'm sure most of you know, have they're publishing a daily basically they have a database, and it's updated every day, I think, with the latest BERs. So the national figures that I've put in here and the Tipperary figures that I've put in are actually 2 days old. So that's I suppose that's the current picture nationally, and the Tipperary picture pretty much follows it. It's a bit lower, a bit higher. The serve area, though, you can see was quite far over to the right-hand side in terms of where the BERs were at. And then if we look then, it took a massive jump to the left after the upgrade. So you can see obviously that people's BER ratings came to the left significantly. So I'll actually go back and forward again just to show you. There's a nice, it's a nice jump anyway there. Well, it could be a typo, or it could be a midnight piece of Excel work gone in there. Yeah, I don't think that E1 should be in there. But that is definitely the profile that we're looking at. Huge shift to the B's and C's. So then we've got the monitoring results compared then to DEAP. So we've got each pair of bars here represents a house. So you've got the theoretical kilowatt hours per year consumed versus the monitored consumption. So you can see there again, like there's a bit of a difference, big difference with some of them, small difference. There's a case there where the actual monitored was higher than what DEAP calculated. But like there's good correlation, but there are differences as you'd expect. On average, there was a 13% difference. So the theoretical value was 13% higher than the actual value, and we did adjust the BER energy consumption for the monitored period using real degree day data from the local weather station in Garteen. So just to make sure that both of them were comparing, say, a warm year with a warm year or a cold year with a cold year. So that has been done with these figures. Then what I've done here is I've basically grouped together by BER rating how does it break down basically. So you can see here, as you start with quite an efficient house, there isn't a huge difference between DEAP and the theoretical and the measured. Whereas as you head up the graph, the difference seems to get bigger just in general. So what you're looking at up here basically is houses that aren't heated properly would probably be a good reason for that. Basically, they're too expensive to heat properly because they're poorly insulated and they're expensive to heat. Whereas the houses on the left-hand side are efficient, they're easy to heat, therefore they're heated well, and they come closer to the DEAP assumptions. So the BER calculates actual energy by I don't know why that title is there, but it's actually different to the content on the slide. Basically, I've just broken down the differences there again from the previous slide. So D1 there, we had a 14%, C3, 23% difference, C2, and B1. So I guess with a larger sample size, you might have some A's in there. It'd be interesting to see what that would be, and you might have some worse BERs as well. Be interesting to look at. I should note here now again, I'm looking at the monitored houses only. SERV has done bill data analysis for a wider group of houses as well, but I stuck to the monitored because they're more accurate for the purposes of this. So secondary heat then, to look at that. So secondary fuel use was quantified by numerous methods. Those of you here yesterday, PJ would have described that, and he had lots of nice pictures of weighing scales and all the apparatus and moisture meters that were used to calculate people's secondary heat use. So a survey was done of the quantity of each fuel type purchased per annum. Survey was done to weigh and quantify the fuel burnt in appliances in each instance that the appliance was lit. The number of lighting instances then was quantified by survey questions, a mixture of survey questions that I would have asked the homeowners to find out how many times per week they light their fire in the shoulder season, so say spring and autumn, and how many in the peak season, so over the winter, do you light your fire once a week or only at weekends, or do you never light it? Or so a mix, I suppose by coming at it from a number of different sides, we managed to come up with quite a good picture of how much secondary heat was being used in houses. We also used fuel diaries that the homeowners filled in to say how much fuel was actually burnt within the fire each time it was lit. Then the results of those methods were compared to ensure that we had a good correlation between them. And I suppose this is just, I stuck it in there just to show the correlation. With any set, you're going to have your outliers, but over 60% of the houses were within the 25% band. So that's comparing the secondary heat calculated by lighting instances of the fire versus the secondary heat calculated by fuel purchased per annum. So that's the differences. Where large differences were identified, we went back and further questioned the homeowners to narrow down again. The secondary heat percentage then, DEAP table 10 assumes that secondary heat energy supplies 10% of the space heat demand for most applications. The analysis shows the below. So basically the green there is your secondary and the black is your main. So this is the actual average percentage of secondary heat for space heat, and DEAP would assume a lower value. So that's I suppose an interesting outcome. The secondary heat fuel breakdown then, we also surveyed what fuel do people actually use. So I broke it down here by appliance type. So we've got stove with back boiler, stove without a back boiler, open fire with back boiler, and open fire without. Now note this one here, the open fire with back boiler, that's only one house. There wasn't many of them, so it's not that particular point isn't a very robust statistic, but it gives us, I suppose, an interesting view that wood is quite popular, but then again, you have to take into account that CERV supported only wood burning stoves, so that wood is going to be popular. DEAP, I mentioned earlier, makes assumptions about temperature, 21 degrees and 18 degrees. So CERV actually included 2 temperature sensors in each house. You had one in the bedroom that was rest of house, and one then, say the main bedroom, and then one in the living room. So I've just included graphs here from the main bedroom. You can see there the red line on the top is summer, so that's not in the heating season. The green one then is the green one is the average, and the blue one then is winter. So you can see in the heating season there, DEAP's assumption of 18 degrees, say, would be a good bit higher than the actual observed temperature. So they're all, say they're in these particular houses, you're under 16 here, you're under 15 in this one at all times. They're 24-hour profiles as well. I should have mentioned that. So 12 o'clock at night to 12 o'clock at night again. So that's what you're looking at there. That again is going to have a big impact on energy calculated for any building. Temperature is key. So here, just I haven't done the analysis now on these to actually tell you, I suppose, what the average differences between what DEAP would calculate and what the actual was for each of these kind of subcategories or sub-assumptions within DEAP. But they're areas that we have data on, and we do intend on doing more analysis. So lighting there again, DEAP makes its own assumptions. We have very strong data now on lighting from 30 houses, which were desegregated electricity. This here is just a graph of the daily profile. It's just one example of the many graphs we have. Domestic hot water again, we've monitored that in 10 houses, so we're going to have more data on that. I have some summary figures here just for the moment. Boiler efficiency, again, we're looking at that in 6 houses. You can see just on this figure here, we've got the seasonal variation in boiler efficiency. The colder months, the boiler works harder, it's more efficient. The solar panels then as well, we're looking at those for 4 houses. So these are just graphs that we have at the moment. We will be looking at these in relative to what DEAP would calculate for the same houses. So to conclude, some analysis remains to be finalised. There are valuable databases there for future work. There have been valuable lessons learned, much more than just comparing DEAP to actual energy performance. That this is, I suppose, the topic of this talk is that, but there's a lot more learned than just that. A blend of soft survey data and hard measured data have offered much more information from the analysis. So data is one thing, but information and learning is what we were looking for, and I think we're getting it in spades. Quantified confirmation that DEAP does differ to the actual. I suppose we expected it would differ. It does. You know, it's not a big surprise, but it's been measured now, and I suppose, you know, we can begin to understand a bit more about why. The secondary heat, quantity supplied versus breakdown, temperature. I suppose there's differences there. There's more to follow in terms of solar, boiler efficiency, domestic hot water, lighting. So DEAP does over-calculate energy consumption, but again, as I said, it is there to save energy. Further analysis is to be done to drill further into each assumption from DEAP. We need to look at renewable outputs and boiler season efficiencies. The data is available. Perhaps there's scope there to widen the sample set to take a look at a bigger set of houses. I think there's value there in pursuing a longitudinal study to extend the analysis, and there's value there in sharpening DEAP to resemble the actual consumption. I think that's about it. Yeah. So thanks very much for your attention, and I don't know, are we doing questions now or at the end? Yeah. Right. So thank you.